Hi everyone. So I want to welcome you to the 5th lecture on mathematical software. And what we're going to be talking about in this lecture is how we implement logic, both on Boolean expressions, and then we're going to talk about how set construction works and set operations like union, intersection, and then we're going to talk about containment as well. So that's a Boolean check for a subset, basically. And then we're going to talk about sums and products and how we can use slightly more sophisticated versions of sum and product to figure out more exotic types of sums and products, including actually sums to infinity is a thing that you can do with this. So let's begin by just recalling that a Boolean operation is an operation that either produces a true or a false. So when I say a Boolean evaluation, I mean some kind of expression that when it's evaluated produces a true or a false. The default behavior of Mathematica, if it can't figure out what it is that you're asking, is to just return the expression unevaluated. So we can see that in expressions like this. So here I've got the pretty obviously true statement that x minus 1 times x plus 1 is equal to x squared minus 1, but Mathematica doesn't actually evaluate that. As in many cases, if you run this and you get back the original expression and it doesn't evaluate, then you actually might need to simplify this entire thing. And when you do that, then it will actually evaluate the left-hand side and the right-hand side after simplification are equal to true. So Mathematica needs to be forced into these evaluations. The second example here is to emphasize the fact that the way that Mathematica thinks about lists as ordered. So Mathematica doesn't have a natural way of thinking about sets. It always thinks about lists. And the way it gets around the fact that sets are supposed to be unordered objects is that it has very easy behavior you can use to sort a list into the correct elements. The other thing is that when we check for it contains all or it contains exactly, that is the subset operations that we're going to introduce later, in that case we don't have to worry about order anymore because it's treating the list as unordered. You'll notice that if I ask it to evaluate a symbolic set, AB is AB the same as AB, then it says true. But if I reverse the order, it actually doesn't say false like it does for the 1, 2, and the 2, 1, because it doesn't actually know the values of A and B. So even if you required it to simplify this, it would still not evaluate it because it could be the case that these things are the same, and it could be the case that they're not the same depending on A and B's assigned values. So in that case, it's not evaluating because it doesn't actually have anything to evaluate on the basis of. So common in procedural languages, and that includes Mathematica, are very easy applications of the logical operators. And those include the binary logical operators like or and then the operator not, which takes a truth value and reverses it. So the not of true is false. The shorthand for not is the exclamation sign. This you would still read as not true. You can use not also if you're evaluating expressions like is 2 not equal to 3? And that's going to return a true because 2 is not equal to 3. So the OR operator is actually defined in this sort of function notation. So it's a binary operator, so it takes 2 inputs, and then it evaluates those inputs and returns a true or false depending on the truth table for OR. And of course you should know that. So OR is going to return a true if either one of the arguments is true. And the quick way to do that in Mathematica, which is much more similar to what you've seen in other procedural languages, is the double pipe. So this is the OR symbol. The AND symbol works the same as the OR symbol. Of course, AND only returns a true if both of the arguments are true. And so the AND of true and false is false. The AND symbol is represented with a double ampersand. So you don't need to write. Oftentimes when you're constructing a Boolean expression, it's not helpful in parsing what you've written down to involve yet another operator with yet more braces. And so it's very common to use these connecting operators, the double ampersands or the double pipes, to connect the expressions that you're trying to evaluate together. So as an application of the outer command that we were in last time, you can actually construct 2 truth tables pretty easily for operators like this. In fact, even complex operators with lots of different values can be constructed in this sort of way. What we're going to do here is we're going to take every possible combination of true and false. We're going to stick it inside the AND function and then produce a table of what the AND produces on those. It shouldn't be a surprise that AND produces true only when the two inputs are true. If you want something that looks more like a traditional truth table, this is just an example of how you can manipulate a table output to make it look nice. So here what I've done is I've taken the output here, which I saved in a variable called AND table, and then I've rendered it in table form, put headings on top of the rows and columns, and then stuck the title AND, which is right here, up on top of the whole thing. So that's just a hint that if you are producing output and you want it to look nice for a presentation or for output into some other document, or just for your own convenience when you go back to something 2 hours later and don't understand what the output was, you can actually take things like table output and put them in a very legible form. Another feature that Mathematica has as a mathematical programming language is that it has categories for different domains that are commonly used in mathematics. So in Mathematica, you can tell it that a variable belongs to the integers, or that it belongs to the real numbers, or it belongs to the complex numbers, or it's a prime number, or it's a rational number. So that lets you assign those values to variables for the use in, say, simplifications. So if you have, for example, something you're trying to simplify and one of your variables is an integer, you can tell simplify that it should simplify with the understanding that one of the integers that you're using is an integer variable. And we'll talk about that more later. What we're looking at right here is a test on a variable. So the fact that these different domains exist means that we have the ability to test if a particular element is in one of those domains. And we do that using the command called element. And this is the typical mathematical element symbol, the little epsilon, which you can produce with a shorthand, but I'm going to show you first what the function looks like. So the command element to integers is asking, is 2 an element of the integers? And that's true. If you want to ask that in shorthand, the way that you produce the element command in shorthand is with what's called an escape sequence. So you would write 2, and then if you hit the escape key, you sort of enter the language that produces symbols, and every symbol in Mathematica has a shortcut. The shortcut for element is EL. So, and you can see here that both elem and L produce the element symbol, and that means that you're actually introducing the command between 2 and integers. Integers. So to produce that element shorthand, you type escape EL escape. So hitting the escape the first time enters you into the symbol language, the escape code language, and hitting escape the second time drops you back out of it. There's a lot of symbols for which you can do this. I don't want to delve into it, but some of the most convenient symbols to use are things like element, or as we'll see later, perhaps we'll look at infinity. So inf produces the infinity symbol. And it's not just the symbol. To Mathematica, infinity is a meaningful mathematical object that can be used in a formula, say, to, for example, take a limit, or as to make one of the limits of summation for an infinite sum into the infinity symbol, which means it will attempt to evaluate the limit of an infinite sum. Okay, so other categories we have available are things like the prime numbers. So this question says, is 4 an element of the primes? If you ask it instead, is 5 an element of the primes, it should tell you that it is. Is pi in the rational numbers? The answer is no. Is square root in the reals? The answer is yes. The nice thing about these structures is they can be used on lists of numbers and not just on individual numbers. And they'll only produce a true if every single number in the list is contained. So when you ask a question like, is the square root function applied to the numbers 1 to 6 in the integers? Well, the answer is no, because 1 and 4 have a square root that is an integer, but root 2, root 3, and root 5, and root 6 are not integers. And so this produces a false. Because what we're really saying here is it the case that, it's actually easier to see if we break out into pieces what's going on here. If we do this step, you can see that we're producing the list from 1 to 6, where we've applied square root to everything along the way. And then when we append the is it an element of the integers to the statement, what we're asking is that list that got produced, is every single element in that list in the integers? And that produces a false. If I ask the same question, if I apply square root to the numbers 1, 4, and 9, is that collection of numbers in the integers? And the answer is true. So this is a very convenient way for constructing Boolean checks that we're going to use to drive if type statements, and then later on controls for loops. The natural analog of logic is the operation of set theory. And so set theory and logical statements are very closely related to each other. And so we're going to talk a little bit about set logic as well. We've already seen a little bit of this with the use of the union command, which strips out repeated elements and then orders a list. Now we're actually going to look at it as its traditional form in constructing new sets out of old sets. So I've defined a list of sets here. You should notice that this particular set I've fixed up so that it has repeat elements, just to see that when we include W in a command, it actually drops those repeat elements. And the three most basic set commands that you should have picked up somewhere along the line in a discrete math class or a methods of proof is that the three basic operations are you can union two sets together, which means you take the set of all elements that belong to one or the other one. So union is necessarily the corresponding set operation to the or logical operator. So the union of two sets is the set of elements that are in A or B, or in this case, U or V. The intersection of two sets is a set of elements that are in the first set and the second set. And then the complement is kind of like the not operator. So the complement is a little bit trickier to understand because you're sort of reversing a set. But you can't take a complement without saying what it is you're taking a complement with respect to. So if you think about a Venn diagram, what you're doing is you're saying, if you're taking the A, the complement of A with respect to B, then you're looking for all of the elements of B that are not elements of A. So if you look at the complement of V with respect to U here, and that's what this command is saying, what that does is it looks at V, and then it produces every element of U that is not also an element of V. So it's a way of pulling two sets apart from each other. So let's take a look at what it does to W. So you notice again here, if I have U and V and W, but W has these repeated elements, you could still do things like union U and W, and you're going to get the same sort of thing where it's going to collapse all the repeated elements down and then sort the result. I do want to point out that the union and intersection operators also have shortcuts like the element operator did. If you'd prefer to work with mathematical notation as opposed to these functions, you could write down U and then escape. And if you start typing in the union, so UN is union, you hit escape again, you get the union symbol, then you could union U and W together, and you're going to get the same result as if you use the union command. Now, again, the shortcut version of this is nice in long, complicated expressions because it's very easy to see what you're doing is unioning two sets together, as opposed to if you have two very complicated sets and then you wrap it all with a union command, it might not be clear what's being glued together with what. So in terms of being able to parse a written statement for other people, like your poor, long-suffering professor who has to grade these things, or you who has to debug whatever it is that you write, when you have complicated expressions and you're working with unions and intersections, it's frequently preferable to use the shorthand notation to make it look like mathematics. So the union operation can be used to construct sets in the same way that the increment operator can be used to, say, drive an index larger and larger. And what do I mean by that? Well, what does the increment operator do? If you start with I equal to a number like 1, and then you increment that operator, or that number, what you're saying is take whatever that number was and add 1 to it. So if you run this again, you should see 2. And if you run it again, you should see 3. What you're doing is you're taking that starting number and you're continuing to increase it every time you apply the increment, right? Essentially, I++ is the same as the command I is equal to I plus 1. And so what that command will do is it will continually increase I sort of recursively. It looks at the previous I, it adds 1 to it, it makes it the new I. You can use the same sort of idea with sets by starting with an empty set. That's like saying A is equal to 0 in some sense, and then continually unioning on a new element to U using this sort of recursive construction. Say, for example, inside of a loop, which we'll see in chapter 7. And so if you continue to union elements on, then A will get larger and larger with the same kind of recursive construction that we see right here with the I is equal to I plus 1. If you do prefer to think more in language that's related to, say, C++ or Python, you can use the append commands instead. But you have to be a little bit careful about what it is that append is actually doing. So if you append to A, so our current set A here is AB, we can check that by doing this. So run A union A, run A union B. We check what A is right now, we have AB. Now, if I want to append C to that set and I run this command, I get ABC out because what it's done is it's appended the element C to the end of A. But notice that didn't actually change A. A is still the set AB. So if you want to make A equal to AB with that element C stuck on the end, you would actually have to use A is equal to this appending step. Okay. And now if you check A, you'll see that now A has saved the fact that C has been stuck on the end. There's a mirror command called prepend, and this matters because remember in Mathematica everything is a list, and in a list order matters, and so prepend means put the element on front instead of the element behind. So if we run this command right now, we should get Z ABC. But notice again, we haven't changed A because that produced a list that had Z on the front, but it didn't save it anywhere. If you want to save the set, you either have to use a construction like we did right here, which is take A and essentially union the element on the end and then save the result into A, so a kind of a recursive construction, or we can use the command append to. And what append to implicitly does is includes the original definition of A in whatever the operation was that you did. So if you started with A being equal to the set AB, and then you ran append to AC, and you check A, well, now that has actually changed the definition of A, okay? So it's kind of confusing, but all of these operations are intended for you to be able to use them inside of a loop type structure so that you can continually add on to the beginning or the end of a list. It's a really useful thing to be able to do. So one strange thing that Mathematica does, given how clear it is about mathematical symbols mapping on to their actual mathematical equivalents outside of a computer environment, is that while it uses element as a Boolean check, it does not use subset as a Boolean check. So if you went and found the subset symbol and you tried to use it, Mathematica is going to read that as you trying to define the inclusion of a variable inside some domain. And that's not quite what we're after when we're doing Boolean evaluations. Typically, the logic with sets that we're interested in is set A contained in set B? That's a question that frequently comes up when we're doing these mathematical questions. So if I want to do that, I have to not use the subset symbols themselves, but instead the Boolean commands contains all, contains none, and contains exactly. So what contains all is, this is a question about subsets. In fact, what it is asking is 1, 2, 3 a subset of 1, 2, up to 10? So the specific question that's being asked here is that. So the big set, the set you're suggesting is the large set, goes on the left as the first entry, and the set that you're inquiring, if it is a subset, goes on the right. And so contains all is how you check, is B a subset of A? Contains exactly is a check for set equality. Remember, two sets are equal if all of their elements are exactly the same. So this is a check for set equality. And it's going to produce a false because, of course, 1, 2, 3 is not exactly equal to the set from 1 to 10. But if you compare the set 1, 2, 3 to the range of numbers that start at 1 and end at 3, then you get a true because range 3 is also the set 1, 2, 3. And these are checks evaluated not as lists, but as sets. So these use set logic, which means just for these operations, the order of the elements in a list doesn't actually matter. And so these force Mathematica to think about lists as actual sets. And these are going to, again, turn out to be extremely useful when we're doing Boolean constructions for if or which type operations, or as control operators for loops later on. The last example here is contains none, and that's actually asking, is A disjoint from B? Which is to say, is their intersection empty? So the question that you ask with, say, contains none, and let's say, I don't know, 1 and 2, and 2 and 3. Well, that's saying, are these sets disjoint? Is their intersection empty? And in this case, the answer is no. They have a 2 in common, so contains none spits out a false. So this is the question, is the intersection empty? So these subset type commands are very often used, like I said, in switch conditions. So for example, things like if and things like which are the next things we're going to talk about. The last bit of logic that I want to talk about here is about decision making or branching commands. And those are functions where we want the function to behave in one way, say, if the input has some property, and in a different way if it lacks that property or has a different property. And so in Mathematica, the if A do this or else do that command is called if, and the multi-case version is called which. And they're slightly different in the way they're constructed, because if looks for a condition to be true, and if it is, it executes one command, and if it's false, it automatically does the other one. Okay, so it's just a two-case setup. And the second part of it always executes if the first part is not true. And so you can see that if Boolean this, that structure. So there's 3 arguments. The first is an expression to be evaluated, which produces a true or false. If the true shows up, then the first command, this, is performed. If the false comes out of the Boolean, if anything else besides true, let's just say that. If anything else besides true comes out of the Boolean, whatever, if it's not even a Boolean thing, what's going to happen is the argument that's in that is going to be executed instead. And so here's an example. So I'm going to produce a statement that's vacuously true. If 2 is equal to 2, then print 2 is equal to 2, or else print math is broken. And we would expect that 2 is equal to 2. If 2 is equal to 2 could somehow produce a false, then we'd be in. We don't need a condition for the second argument, because the second argument always fires unless that expression evaluates as true. And so exactly one of these cases will fire. The first if you get a true, the second in all other cases. But maybe we have 3 or 4 conditions that we want to apply. So the command which is good for that, but there's a slight subtlety we have to be careful of. So this is an example of the which structure. So in a which, you have an expression to be evaluated for true or false, and then the thing that happens if it's true. Then you descend down to the next check. You check the expression for true or false. If it's true, you do the thing next to it. If it's false, you move down. It's possible in a which command to produce something that does nothing. And sometimes you want that. Sometimes you want a command that only does something if something off of a list of Boolean expressions or Boolean evaluations throws out a true, and otherwise you don't want anything to happen. But oftentimes there is a default that you want to trigger, and the example that I've got written here should show you exactly how to do that. So in this which command, what we're going to see here is that we have a descending order of things that are going to happen. So actually, let's take this out first, and I'll show you what this does. So this which command is going to say, if 2 is equal to 3 produces a true, then print math is broken. And if 2 is equal to 0, then print the only number is equal to 0. And if you run this, nothing happens. There is no default condition here, which is perfectly happy to run through every case, and if it doesn't find anything true, it just stops. If you want something to happen by default, you have to make sure that you include the very last line of the function includes true as the condition, because true always evaluates to true. There's nothing to evaluate. So the which at the very end will see that true, and then it will interpret it as the thing that fires because nothing else did. And so if you actually run that command, then you get exactly what I just did, which is the default print. This is the default that runs if nothing else triggers. So this is a trick to make sure that when you're looking at a which command, that you get something at the end that does what it is that you want it to do. Okay, that's a very powerful feature of which, by the way, that it can do one or the other. Okay, so that's sort of an introduction to the set logic and the Boolean expression that I wanted to talk about, and also decision-making functions like if and which. The next thing that we're going to be talking about is going to be sum and product, but that's going to be in a different video. So I will talk to you guys shortly. Take care.